6.8, the divergence theorem. Stokes' theorem we saw was a generalization of Green's theorem. The divergence theorem is another generalization of Green's theorem, yet quite differently. Overview of theorems in calculus. There is a fundamental theorem of calculus. Here is the part 2 of that theorem. The evaluation, that if we have a nice function, let's look over here, a nice function which has a derivative, we can integrate that derivative and find that summing up the values of the derivative over an interval can be evaluated simply by looking at the function at the two endpoints. So here we have the boundary evaluation and then the interior evaluation. The first generalization that we had of that was in the fundamental theorem of line integrals. For FTOC, we need a function which is differentiable. For FTOLI, we need a vector field which is conservative. That means it has a potential function. So this line integral is from the beginning of the curve C to the end of the curve C, just like A is the beginning of the interval to the end of the interval. And that we look at the antiderivative to find the value of the integral. Here, this integral, we look at the potential and look at the ending point and subtract away the value of the potential at the beginning point. So we're able to relax the fundamental theorem of calculus by expanding the interior from just being given in a single variable to two variables, so a region in the plane, D. And then Green's came in two different forms. Here's the circulation form. We can see circulation on the right-hand side as this line integral, the boundary integral, is looking at a vector field in the direction of the curve, so that's circulation. So boundary related to interior. This interior has an integrand which can be equated to curl dotted in the k direction. K is the unit normal to this domain of integration. Green's also comes in a flux form. This is the form that the divergence theorem is going to generalize. We'll come back to that in a second. Looking at Green's, the circulation form, that generalized from removing the restriction that the enclosed region, C must be a closed curve, enclosing a flat region D, relaxing that D must be in the plane to it can be any surface, and then take that surface and look at the boundary of that surface. And then you have an interior evaluation set equal to a boundary evaluation. And then the integrands are identical, given that this integrand can be written down as curl dotted with K. Nice. Okay, so let's come back and let's look at the other form of Green's, the flux form. So here the circulation is looking in the tangent direction. Orthogonal to the tangent direction would be the normal direction, so this is a flux integral. This is flux across a curve C. In order for Green's to work, you want to have counterclockwise orientation, so that we get an outward orientation across the curve C. So from the inside to the outside. Okay. Looking at the integrand, since our vector field F vec would be assumed to be a 2 vec, P and Q. P is the x coordinate, Q is the y coordinate, so partial P in x and partial Q in y, sum those up, and then that's going to give you the divergence of that vector field. So this integrand is a divergence quantity, a scalar quantity. So how do we go from Green's, the flux form, and come up with the divergence theorem? Well, just like Stokes was to relax the domain requirement, we're going to do the same thing. However, what we're going to do is we're going to increase the count on the integrals from 2 to 3, and likewise increase the count on the integrals from 1 to 2. Going from 2 to 3, this is going to become a solid. The interior will be a solid, so that a line or a curve increased up by 1 becomes a surface. So just like this curve has to enclose that region, we're going to have in the divergence theorem a surface enclosing a solid. Let's look at that. So here it is. Let's write it down. And let's start on the right-hand side. And then we have a surface integral. That surface S needs to be a nice surface, so it needs to be smooth, or if it's not smooth, at least piecewise smooth. And then secondly, importantly, it must be closed. So this is a closed surface. And if it is closed, then you look inside of it and you get a solid. So that's the interior. 1, 2, 3. A triple integral over the solid. How are these related? This is the boundary of that solid. Boundary, interior. All right, so what are we doing? We are extending Green's in its flux form. Let's look on the boundary. We're taking the flux across the line integral. To go from Green's to the divergence, the boundary is now going to be a surface integral. So this is going to be flux across a surface. We're going to want a vector field, and then we're going to take that vector field and then dot it in the normal direction. That's going to be our integrand, an integrand in a surface integral. So our differential is the surface area differential. And again, this quantity here is the same thing as that vector quantity. Good. So we have a flux integral as a surface integral corresponding with this flux integral. That closed curve C in the plane closes this region D in the plane. This closed surface in 3 space is going to enclose this solid E in 3 space. The integrand here in Green's can be written down as the div. Over here, this vector field must be defined on the surface S. So that vector field has to be a vector field in x's, y's, and z's. And so when we take the divergence of that vector field, we're going to have a p partialed in x, a q partialed in y, and an r partialed in z. That is the divergence. So div of the vector field, that's a scalar quantity. And that's the entire integrand, which we want to evaluate over this solid. And then a small piece of the solid is a tiny volume element. And so we integrate with respect to the volume differential. Good. So there's the divergence theorem. Here's a nice little picture. The picture is really shaped in a way to help motivate the baby proof that is provided in the book. Again, I'm not going to go over it. And essentially they break it up into pieces. Here you want to think of this as a rectangular box where you can look at flux across this and then flux across that and so forth. Okay, so let's play around with it a little bit. Walk through this example where they verify, meaning that they look at an interior integral and a boundary integral. So we need the vector field, and the vector field that they give us is x minus y, comma, x plus z, comma, z minus y. And then the surface is the top portion here in blue, the circular top. And then S2, and then that's the cone. So S1, the top, and then S2, the cone. And then the cone is described as x squared plus y squared equals z squared. So that's x squared plus y squared, which is just r squared. R squared equals z squared. So if you look at r's and you look at z's, then the cone is going to trace out. It's going to require an angle phi of 45 degrees, or this line here is going to have a slope of 1. They give us a restriction on z's. Z's are from 0 to 1, so the height of the cone is going to be 1, and the radius at the top of the cone is also going to be 1. Which means that our circle, S1, is a unit circle, everything inside of a unit circle, in the z equals 1 plane. So that's S1. All right, and I think that's where they start. Nope, they start by looking at the interior evaluation. Let's go back and look at our vector field. Here's our vector field. Let's quickly do the divergence of that vector field. So here, partialed with respect to x, you get 1. Partialed with respect to y, you get 0. Partialed with respect to z, you get 1. So div is a nice constant 2. That's really simple. So div is just 2. Pull that to the front, and then you have the volume of the solid, and the solid is this cone. And then there's a formula for the volume of a cone where the height and the radius are both 1. We've already gone over that. So you get 2 times pi over 3, or 2 pi thirds. So now we want to do the surface integrals over the top, S1, and then over the cone, S2, and verify that those two values sum up to 2 pi over 3. Okay. So again, if we take a unit circle, S1, then we can parameterize that surface by using sines and cosines. Let's go cosine u, sine u, and then we want this to occur in the z equal 1 plane. But then if we only did that, we would remain on the boundary of that surface. We also want to capture everything inside, and therefore we allow the radius to vary, v, from 0 to 1. Looks like I copied it wrong. So here, that is u, 0 to 1, and then u as theta from 0 to 2 pi. So I copied that wrong. Okay, you can compute partials in the u direction, partials in the v direction. This is something that we've done many, many times, so I'm just going to gloss over it. Compute that cross product. The vector field, well, when you actually do compute out this cross product, the first two terms are 0, and so it's just the last term that's alive. And the vector field was z minus y, so you get 1 minus u sine v, z minus y. And then that dot product would give you this, and then you can verify that you get that quantity. All right. So evaluated on the boundary, which is a portion of the boundary, is this circular disk. So far we have pi. Then along the cone, if we want to compute the surface integral over the cone portion, we need a parameterization of the cone. So let's draw a little triangle here with slope 1. So this is r, that's z. And then you want to think about taking a point And then any point that you pick, that's going to be at some height z. So there we go. We're already on the books for z. Let's call that, what do they use? They use u. So let's use u. That's u. And then that's going to be the radius. And then at that point, you want to circle around. So take u, u. And to circle around, you can do cosine v and then sine v. So this parameterizes the cone. And then what do we want u to do? We want u to go from 0 up to 1. Those are the quantities for z. So u is from 0 to 1. And then we want v, acting like theta, to make a full revolution, 0 to 2 pi. Excellent. And then you can go ahead and plug and chug. Take partials, cross the partials, come up with this quantity. We've gone from a formal surface integral over the cone, parameterized, and able to write this out as a regular double integral. This piece here has been computed. You've verified that. And then the f-vec, you're going to have to go back and you're going to have to look up how the f-vec was defined. But that's simply plugging in for x, plugging in for y, and plugging in for z. Fantastic. And again, the nice thing about the Stokes theorem and the divergence theorem is that you can make a choice to evaluate either on the interior or on the boundary. So applying the divergence theorem, we're presented with an integral to evaluate, where it's a surface integral. And then luckily that surface is a cylinder, but it includes both the top and bottom. So draw a cylinder. Think about the walls, but then they tell you, hey, wait a minute, you have both the top and the bottom. In other words, it's a closed surface, which is piecewise smooth. And then the vector field itself is gnarly complicated. So instead of dealing with that mess of working on the surface, which is closed, maybe you want to push to the interior. And since this is a flux quantity, as you're crossing over, then you, on the interior, you would, by the divergence theorem, want as integrand div of this complicated vector field. And we can quickly take a look at what div of that vector field is. So you look at the first portion, partial it in x's, that guy goes away, and you get x squared. Second portion, partial it in y, that goes away, and you get y squared. And this portion, partial it in z, that goes away, and you get 1. So that's a lot simpler integrand to work with than this complicated integrand. And again, I'm pointing out very strenuously that you have to have the right conditions. All right, it's a surface integral, but you need the surface to be closed. So it does have walls, and then it has a top and it has a bottom. So it is indeed closed, and it therefore encloses a solid E. So then we have the triple, where the integrand is going to take this nice form here, and we can go ahead and evaluate that. Note that they are changing from rectangular to cylindrical coordinates in evaluating this, since x squared plus y squared is the same thing as r squared. Fantastic. Thank you, guys.